Hi, I'm Dan Cunnington, and on behalf of my collaborators, I will present our paper, Neuro-Symbolic Learning of Answer Set Programs from Raw Data. Neuro-Symbolic AI is inspired by Kahneman's dual system theory, and the goal is to combine the benefits of both fast and slow style thinking. Here we assume System 1 is a neural network that can perform fast perceptions from unstructured data, and System 2 is capable of complex logical reasoning. Note these systems are complementary, and together they provide benefits that are lacking in each system individually. One approach to integrate System 1 and 2 is Neuro-Symbolic reasoning, which focuses on using logic to improve the training of neural networks, by either constraining the neural network to satisfy some known background knowledge, or training with weaker supervision that reduces the requirement for labelled data. However, the key question is, where does this knowledge come from, as currently it is manually engineered by humans? Therefore, we replace the logic component with a symbolic learner to enable end-to-end neuro-symbolic learning. The goal is to train both systems simultaneously, which is challenging because the symbolic learner is not differentiable. Our approach, Neuro-Symbolic Inductive Learner, or NSIL for short, achieves this in an iterative fashion. So, we have a neural network that we wish to train to classify images into latent concepts, and we also have a symbolic learner. The neural network is implemented within a neuro-symbolic reasoner. In this paper, we focus on learning answer set programs due to their ability to efficiently express solutions to complex problems. We therefore use ILASP or FastLAS as our symbolic learner and NeurASP for the neuro-symbolic reasoner, given the common base of ASP. As input, we have a collection of images and the target label for a downstream task. We also have a background knowledge, which includes the possible space of latent concepts and a search space of possible rules. As output, we have a hypothesis H and a trained neural network. We initialize the system using a bootstrap stage, which returns the shortest H in the space that is defined for each output label in the dataset. This means there must be a choice of latent concepts that output each label for the learned H. We then use this H to train the network in NeurASP. To give a brief intuition, NeurASP trains the network to maximize the softmax probability of latent concepts that are in the answer sets of the ASP program. And this program includes the candidate H and the downstream label. As an example, for an MNIST addition task, where the inputs are MNIST images and the label is the sum of the two digits, assuming we have the correct H, the neural network would be encouraged to predict concepts that lead to the sum. In this example, the neural network would be trained to predict 0 and 6, 1 and 5, 2 and 4, etc. for these images. In our system, we iterate over the training set to train the network in NeurASP, whilst the ASP program stays fixed for a given H. Now, you might be wondering what happens if we learn the incorrect H during the bootstrap stage, which is likely to happen in practice. Therefore, we create a set of corrective examples for the symbolic learner, which enables the symbolic learner to either retain the current H or learn a different one based on the current system performance. Corrective examples associate latent concepts with a downstream label. We introduce a pair of corrective examples for each combination to represent the label positively and negatively. For MNIST addition, with concepts 2, 4 and label 6, positive means label 6 should be output for concepts 2 and 4, and negative means label 6 should not be output, and a different label chosen instead. The examples are weighted, and the higher the weight, the more the symbolic learner is encouraged to cover that example with the learned H. We link the weights of each example pair, and the goal is to maximize the weights of the positive examples that have correct combinations and minimize the weight of the corresponding negative examples. The symbolic learner has access to all the combinations of corrective examples for each pair of latent concepts and each downstream label. We tune the weights of the examples on each iteration using two sources of information calculated on the training set. The false negative rate of each downstream label, which is high if the system performs poorly when classifying training data points with that label. We use this as a negative weight signal. The neural network confidence on the training set is used as a positive weight signal, which is high if the network is trained well. We firstly apply the false negative rate via an abduction that calculates all possible concepts that output each label, given the current H. The negative examples for these combinations receive a weight update, and the corresponding positive weight is set to 0. We then apply the neural network confidence by increasing the positive corrective example weights where the neural network has predicted those latent concepts and the label matches the downstream label in the training set. Please refer to the paper for more details on how these weights are calculated. The intuition is, when the system performs poorly, the false negative rate will be high, which will encourage a different hypothesis to be learned, and when the system performs well, the neural network confidence helps to retain the current hypothesis with a positive signal. To evaluate NSIL, we run a forward pass through the entire architecture and compare the downstream prediction to the ground truth label. The evaluation aims to address the following questions. How do we compare to the closest existing system, MetaABD, which also trains both a neural network and a symbolic learner? How do we compare to end-to-end neural networks? And finally, can we learn more expressive knowledge, including negation, choice rules, and programs with multiple answer sets that would be difficult to learn with other systems? The first task is the recursive arithmetic task. The input is MNIST digits arranged into lists of length 2 to 5, and the label is the addition or product of the digit values. We use the same background knowledge and search space encoded into ASP, and the goal is to train the neural network to classify MNIST digits and learn a recursive hypothesis to compute the sum or product. The results show that we outperform MetaABD on both the sum and product tasks. The accuracy at one metric shows the best network accuracy achieved, and the MAE metrics show the mean absolute error on test sets with increasing list length, which shows the learned programs can generalize beyond the list lengths observed during training. We outperform MetaABD on all metrics, learn the correct hypotheses, and train our networks with significantly fewer training epochs. Okay, now we demonstrate learning more expressive knowledge with negation as failure in a larger search space. The search space contains rules to learn addition and a new E9P task, which is, if the first digit is even, predict the value of the second digit, otherwise predict 9 plus the second digit. This is to demonstrate that the search space does not have to be engineered exactly to solve a particular problem. Note the range of output labels is the same in both tasks, which is harder than addition and product, shown in the previous slide. This is where we compare to neural models. We use an end-to-end CNN, the blue line, and two variations of a concept bottleneck model, the green and red lines. The purple and cyan lines consist of a CNN LSTM attached to neural accumulators and neural arithmetic logic units. We also compare to MetaABD on the addition task only, as it is unable to learn negation in the E9P task. With 100% of the data, NSIL as the black line outperforms all models. Reducing the training set further to 10% and 5%, you can see NSIL significantly outperforms all the baselines. In these cases, the corrective examples work effectively when the network is undertrained, and NSIL can explore the search space until the neural network becomes more accurate. For the E9P task, NSIL also outperforms the baselines, especially as the amount of training data reduces. Here, we have to search the space to find the correct H, even with 100% of the data. The correct H is not learned on the first iteration. Finally, NSIL can learn expressive knowledge, including choice rules, that enables the learned programs to generate multiple answer sets. Here, we demonstrate learning a program that can generate all the hitting sets of a given collection with a certain size, despite learning from binary labels that only indicate the existence of a hitting set. This would be very difficult to achieve with other systems. On the right-hand side, when comparing the accuracy of NSIL to neural models on the simpler decision problem, NSIL also outperforms these neural models. Please refer to the paper for more details on this experiment. To conclude, we have introduced NSIL, a novel method of simultaneously training a neural network and a symbolic learner. NSIL is capable of learning complex knowledge from raw data that would be difficult to learn with other systems. We've demonstrated the corrective examples enable NSIL to converge to the correct solution in large search spaces. And finally, NSIL outperforms the closest existing system, MetaABD, and also outperforms neural models in terms of accuracy, interpretability, and data efficiency. Thank you very much for listening, and many thanks to the collaborators listed on the slide.